Okay, so I thought we'd just cover a few of the key points from the last lecture. This is maybe something like a cheat sheet, so you can go back and review the things as necessary. So the first thing we covered was the Zariski topology on k to the n. So here k is an algebraically closed field. And this involved thinking about the open and closed sets, and the closed sets are the algebraic sets, algebraic subsets of Kn. Those are the closed sets in the Zariski topology. The open sets, we didn't describe all the open sets, but we gave a basis for the open sets in terms of the principal open sets. So the algebraic subsets are the vanishing points, the sets of the vanishing loci of ideals in the polynomial algebra. And the principal open sets are the places where a given polynomial is non-zero. So every polynomial in n variables in the polynomial algebra k t1 through tn defines a principal open set, namely the points where that polynomial, thought of as a function on k to the n, does not vanish, is non-zero. So those were the important points in the Zariski topology. The other thing we talked about is the affine algebra of an algebraic set. And so there was a definition. So there was a definition of the affine algebra of an algebraic set. So this definition gives us, this algebra gives us an intrinsic characterization of these algebraic sets. So a given algebraic set can be embedded in different k to the n's, in different vector spaces, but it will still have the same affine algebra. There was also the definition of affine k algebras in general. And this was a finitely generated k algebra, finitely generated as an algebra with no non-zero nilpotents, so it's reduced. And we saw this bijection between k algebras, between affine k algebras and algebraic. So this dictionary, you should think of this as a dictionary. It's very important because we can go back and forth. Usually we start with some sort of geometric problem and translate it into algebra, but sometimes we go the other way. And another important set of topics were affine varieties. So we had the notion of regular functions and general varieties, which were glued from affine varieties. And we also talked about projective varieties. So if you don't know any other non-affine variety, you should know projective varieties. So they're the most important examples of non-affine varieties. So you define them by first considering projective space, p to the n, and it's Zariski topology. And then the projective varieties are closed subsets of projective space in the Zariski topology. You can define them in terms of like homogeneous polynomials. So you should know something about homogeneous polynomials and ideals. And then we also mentioned a few other topics. So I'll include them here. So there is reducibility and irreducible components. There was products, which I believe you talked about more in the TA session. And there was morphisms between varieties. So I gave kind of a confusing definition. there's maybe a simpler definition to work with. I think you might have talked about in the TA session. I may write up some notes about that and post it on the website. But for affine varieties, there's a easier way to think about morphisms, and also for projective varieties. And finally, we talked about dimension of varieties. We started with the dimension of irreducible affine varieties. Then we moved on to the dimension of irreducible general varieties, not necessarily affine. And then we defined the dimension of an arbitrary variety, irreducible or not. Okay, any questions so far? So I'll post this on the website so that you guys have it. Okay, so let's move on then. If there are no questions, feel free to interrupt at any time if you have a question. So the next thing we'll do is I want to finish the lecture about algebraic geometry. There's just a little bit more to mention, and then we'll move on to the second chapter of Springer, which is the first properties of linear algebraic groups. We'll define linear algebraic groups properly and start talking about what they are and some of the first results. So let me share this screen. Right. So this is where we approximately where we stopped last time. So I wanted to mention, so there's a section in Springer with some results on morphisms. There's lots of results there. We'll go back if we need any of them. But I just wanted to mention this result. So if we have a map of affine varieties, x to y, then as we saw before, there's a corresponding algebra homomorphism from the affine algebra of y to the affine algebra of x, so it goes the other way. Then we have the following results. So first of all, if the map of algebras is surjective, then the image of phi inside y is closed. So here, this is another example of this dictionary. So this algebraic property of this map of algebras being surjective translates into a geometric property, namely the image of this map is closed. On the other hand, if the map is injective, if this algebra homomorphism is injective, so its kernel is just 0, then the image of this map here, the geometric map, is dense. So dense means its image intersects every open set. So its image is pretty much everything. Like there's some things that are not in the image, but the closure of the image is everything. So the other fact to mention is that, oh, sorry, my handwriting is kind of bad here, but if the variety we're mapping from, if x is irreducible, so we talked about irreducible topological spaces, if x is irreducible, then the closure of its image is also irreducible. And the dimension of the closure of its image, so the dimension is well defined, it's easy to define for irreducible varieties, is this dimension is less than or equal to the dimension of x. Okay, so those are some results. As I said, there are many more results on morphisms in Springer. We'll go back and use them as necessary. I'll try to say something about them.
Can I have a small question?
Sure.
About this? Why it is only less or equal? The closure seems intuitively must be at least the dimension of x.
So it's the dimension.
Oh, it's the image.
It's
Okay.
the image. Yeah.
Okay.
Yeah. It's the image. Yeah, I know my handwriting is kind of bad and small here, but it's when we map, we can never gain dimensions. We always lose dimensions. Okay, thanks for the question, Tal. Anybody else have questions? Okay, let's go on then. So I wanted to say a few things about F structures and F varieties. So I think the way I'm designing the course, it won't be super important. Some courses on linear algebraic groups really emphasize this this notion. Other courses set things up in terms of scheme theoretic language. So for example, Milne, where these sorts of things aren't really so relevant. So I'm not thinking of talking too much about F structures and F varieties. However, it's something that is in this general area, so it's good to mention. So the idea is from the very beginning, we took K to be an algebraically closed field. So that's a very, algebraically closed fields have very nice properties, very nice structure. There's a lot we can do with them, and some of that breaks down when we remove the assumption, when we drop the assumption of being algebraically closed. So we often need to consider a subfield of K, which is not algebraically closed necessarily. So the canonical example here that's motivating for this is thinking about R inside of C. So R is not algebraically closed, C is algebraically closed. And if we have a affine algebra over K, so as we saw last time, any affine algebra is the affine algebra of an algebraic set. So we can say that A is the affine algebra of X. And this is over K. Then we say that an F structure on X is an F subalgebra A0 of this affine algebra satisfying the following two properties. So first of all, A0 is a finite type over F. So it's finitely generated as a F algebra. And second, if we extend scalars, so so this tensor product extends the scalars from F to K. So A0 is only has a structure of an F algebra, nothing with K. But when we do this tensor product, we produce a K algebra, and it naturally embeds inside of the affine algebra A, K brackets X, and that's because A0 was a F subalgebra of A. And we require that this map, multiplication map, or if you want, you can think about it as extension of scalars, we require that this map is an isomorphism. And moreover, the set of F rational points of X is the set of F algebra homomorphisms from A0 to F. F is, the field F. F with its usual F algebra structure. And so if you want to get a handle on this, you can think about this example from Springer. This is the affine algebra we're considering. So polynomial algebra in two variables mod this relation t squared plus u squared equals 1, or t squared plus u squared minus 1, the ideal generated by that. And we have these two F subalgebras, so F being the real numbers. And these are two different R structures on X. So that's something you can think about. So so that's the claim. You can think about why that's true. But when we compute the F points, the R points, when we take the first one, we get the circle S1 inside of R2. And if we compute the second one, then we don't get any R rational points.
Can I ask a question?
Sure, go ahead.
In A0, A and B are like T and U?
So, oh yes, yeah, that's right. So I didn't say that.
Okay,
thanks for pointing that out. So this, just give me a second here to make sure I know what I'm doing. So yeah, so let me write a comment. There we go. So A is the image. Yeah, the reason I didn't write T and U is because A is actually the image of T in K brackets X. So T, I want to think of T as something living in this polynomial algebra. And when we take this quotient, it maps to something, and that something is, we call A. And one more text box. B is the image of U. Okay, thanks for pointing that out. Right. So we can extend these notions of F structures to affine F varieties and to general F varieties. Okay. So I think that's all the algebraic geometry we need for now. We can move on to linear algebra.
Can you explain the claim?
Hmm?
What are the results on the claim? I didn't understand the intuition. The claim that you didn't say.
I didn't say. I'm going to let you think about it. Yeah. It's not, if you're interested, go ahead and work it out. But if this doesn't make too much sense for you, it's not crucial for the rest of the class. If it happens to be, I'll remind you. All right. So any more questions? Okay. So then let me change PDFs again. Oops. So, all right. So let's get started with the chapter 2 of Springer. So first, properties of linear algebraic group. So first, I want to start with a comment, a pretty basic comment. So again, K is an algebraically closed field. Now there's a unique zero-dimensional connected K variety. So if we think about the point as a topological space, then that's a K variety, and it corresponds to K as an affine algebra over itself. So it's an affine K variety corresponding to K as an algebra over itself. This is kind of trivial. So this is what it says here. And if we have any K variety X, there's always a unique map to a point. So that's something we can always do. Right. So that's just a comment that we'll need later on. Okay, so now we get to the definition of algebraic group. We saw kind of a preview of this definition in the introduction last week. So an algebraic group is an algebraic variety. Now we know what that is. Equipped with an operation, a multiplication map mu from G cross G to G. And I'm going to write it just with juxtaposition. So x comma y goes to xy. And it satisfies the group axioms. You probably all know what those are, but I'll rephrase those group axioms in a second. And as part of the group axioms, we know that there's an identity. And we think of this identity as a map from the point into G. So it just picks out an element of G. But I think it's conceptually important that we think about it as a map from a point to G. And I might be a bit loose with notation. I might denote 1 sub G both for this map and for the image of this map, which is an element in G. And there's also an inverse, G to G, which takes X to X inverse. So because G is a group, every element has an inverse. And these maps are, all these maps, so mu, especially mu and I, one is, this map is pretty straightforward, but these maps all have to be morphisms of varieties over K. So all the structure is reflected in these maps. Okay, so that's an algebraic group. We're also interested in the notion of a linear algebraic group. So this happens if the underlying algebraic variety of G is affine. So if Yeah, so we in general, the underlying algebraic variety of G is not assumed to be affine, but if it is, we call G a linear algebraic group. And we'll see the reason it's called a linear algebraic group later today, as opposed to affine algebraic group. Okay. So you can recall from the last lecture that any affine variety X is completely determined by its affine algebra of functions, K brackets X. So we saw that the both the X as a set can be recovered from the affine algebra by looking at maximal ideals, and also the Zariski topology on X can be recovered from K brackets X by looking at ideals. And so somehow, so based on this philosophy, this dictionary that for affine varieties, everything can be translated into algebras, we have the fact that the group structure in any linear algebraic group can be expressed in terms of its affine algebra K brackets X. So all the information that we need is encoded in K brackets X with extra structure. So to see how this works, let's recall the group axioms. So there's 3 of them.
Just what do you mean by K bracket G? The G is the
It's the affine
variety.
algebra of G as a
Okay.
variety. It's not the
Okay.
group algebra. We'll say something about the group algebra in a little bit. Yeah, that's a good point, but it's just we think of it as an affine variety, and this is its affine algebra. Okay, so what are the group axioms? There's 3 of them. First, there's associativity, so the operation has to be associative. So you're probably used to seeing this as the following identity. If we take 3 elements and first multiply these 2, and then multiply by G, then that's the same as multiplying these 2 and then multiplying by K. And you can express this as a diagram, as a commutative diagram. So you take 3 elements in G, we multiply first the things in the first 2 slots, and we just keep the last one just tags along, and we end up here. And then we multiply the resulting 2 elements, so that corresponds to the right-hand side. Or we can first multiply the last 2 coordinates and let the first one tag along, and then multiply again. So that corresponds to the left-hand side. And the fact that we have equality here is equivalent to saying that this diagram is commutative. Okay, so that's the associativity. There's also the unit axiom. So the unit axiom in maybe the way you've seen it in a course on group theory is just that if we multiply any element on the left or on the right by the identity, we get that element back. And we can express it as a diagram in the following way. So here, this map is inclusion into the first coordinate, and the second coordinate will just be the identity. Here, the identity in G. Here, we include into the second coordinate. The first identity is the identity in G. And if we go around this way, or we just do the identity map on G, then we get the same thing. And this diagram commutes, which is equivalent to these equalities here. Okay, and there's also the inverse axiom. So the inverse axiom says that if we multiply any element by its inverse, either on the right or on the left, we get the identity. And to express it, we get this slightly more complicated diagram. So this is the diagonal map. So little g goes to little g comma little g here. Same thing here. I guess I didn't write it. And I guess I didn't write here. This is the multiplication map. And so, and this is also, let me add that in real quick. The map mu. I guess most of you are familiar with LaTeX, so I'm just going to write it this way. this is also the diagonal map. So this is, and here we do the inverse map in the first coordinate and just the identity map in the second coordinate. Here we do the opposite. And this map takes all of G to a point. As I said before, there's a unique map to a point, and then we do the identity map here. So if you think through this, you'll see that the commutativity of this top diagram and this bottom diagram are both equivalent to, so this top diagram corresponds to this equality, the bottom diagram corresponds to this equality.
Is there any particular reason why you factor the unit morphism through the points?
Yeah, there is a reason. So we'll see this reason soon. One reason is to get you used to thinking in this way, like separating out the different maps. But we'll see another reason probably in the next page. Any other questions about these diagrams?
Yeah, I'm not sure you answered, but maybe you answered by this last answer, but is there a particular reason why you formulate these things in diagrams?
Yeah, there is. You'll see soon. I mean, first of all, I personally like diagrams. I think they look cool, but there will be a reason when we talk about the affine algebra of a linear algebraic group. Yeah.
Okay, thanks.
Okay, so here we go. So if we have, so I said that the affine algebra encodes. So any structure we have on affine variety, we can encode it in terms of its affine algebra. In particular, if that affine variety is a group. In other words, if we have a linear algebraic group, then we get some structure on the affine algebra for the group. So first of all, this map mu induces a coproduct on the affine algebra. So these are all of these things here are affine varieties. And we saw that the induced map on affine algebras, it goes the other way. So we get algebra homomorphism from k brackets g to k brackets g to enter k brackets g. And this is, more concretely, this is nothing but pullback of function. So if we have a function, think of a function emanating from G to our base field K, then we can precompose by mu to get a function from G cross G to K. And the affine algebra of G cross G is this tensor product, as we talked about last time. So we get this pullback map. And this induces the map. So I wrote an arrow in one direction, but really we also get if we had this coproduct, then we get a map G cross G to G. I'll say something about that later. But for now, let's think about going in one way, in one direction. So we had this identity. So picking out the identity element of G. So this corresponds to the co-unit map. So from kg to just the field K. So recall, as I said in the beginning, the affine algebra of a point is just the field K. And then this inverse map, G to G, corresponds to what's known as the antipode. I think actually Springer uses different notation for the antipode and maybe for the co-unit, but this is what I'm used to. So this is what we're going to use in the class. Okay, so great. So we have these maps. Now, what about so these maps are part of the data, but they need to satisfy certain constraints. They need to satisfy these axioms we just discussed. And the associativity axiom corresponds to what's known as the co-associativity axiom on the affine algebra of G on k brackets G. And it's just this map. It's just this diagram being commutative. So one can write out the co-associativity axiom in terms of just symbols. So you can figure out notation for this map delta of f. So there's this thing known as Sweedler notation for Hopf algebras. You can use that to write out what this axiom is saying in terms of some formulas, but it's cleaner. I think it's unambiguously cleaner to just write it as a diagram. And this diagram is obtained just from the associativity diagram by replacing G with K brackets G and reversing the arrows. So mu becomes delta, and products of varieties become tensor products of algebras. Right? So that's the co-associativity axiom. And the unit axiom becomes the co-unit axiom. And the so we have that. Yeah, I mean, it's just the corresponding thing to what we wrote before. And the inverse axiom becomes what's known as the hexagon axiom. For some reason in this theory, it's known, well, it's not for a random reason. It does look like a hexagon, but it's just coming from the inverse axiom. So, so here, this is the coproduct. And this is, so one important thing. So the diagonal map, we have the diagonal map from G to G cross G on the page above. By the way, maybe I didn't say this, but these notes should already be on the website for the class. So if you prefer to have them on your computer and scroll back or peek ahead at your own speed, feel free to do so. So so before we had the diagonal map from G to G cross G, and that actually becomes the multiplication map. So we take KG tensor KG. That's so K bracket G is an algebra, so it means we have a multiplication map. Given any two elements in KG, we just multiply them together. That's all this map is doing. Multiplication is bilinear, so it factors through the tensor product. And what do we have here? So here we have this map eta, that's the co-unit, and then K, what's this map? Well, any K algebra has a canonical map from K. It's, yeah, canonical K algebra homomorphism from K, and that's all this map is doing here. It's the analog of every K variety having a map to a point. Okay, so those are the translations of the axioms from groups to algebras. Does that? So I think Ido and Tao, you both had questions about whether why it's useful to phrase the group axioms in terms of diagrams. Does this page answer your question more or less?
I asked different question. The question I understand right now, but I asked why you factor the unit. Why does it? Why it help you?
Yeah, I think it's because because then you factor this in terms of the co-unit and this this canonical map.
Okay, you wanted to express this as a terminal object. Okay.
Yeah.
Okay. Yeah.
And Ido, what about you?
Yeah, I'm happy. Thanks.
Okay, great. All right, so so we can kind of take all these things that these translations and bundle them together into a new notion, which is called a Hopf algebra. So a Hopf algebra over K is, first of all, a K algebra, H, and it's equipped with these maps. So it's very important that these maps are K algebra homomorphisms. So first of all, we have the coproduct, H to H tensor H. H tensor H being a K algebra with the coordinate-wise multiplication. eta from h to k, and oops, this should be an h. Sorry, I should fix that right away. So actually, correction. S goes from H to H. I'll try to fix that and then upload the new version. So, and these K-algebra homomorphisms satisfy the co-associativity, co-unit, and hexagon axioms that we just saw. So that's all that a Hopf algebra is. So it's you can think of it as a group. It's hard to use the terminology because it's all this terminology is overloaded, but you can think of it as kind of a group inside the category of K algebras. So, or it's just a translation of these group axioms into a different setting.
Does H have to be finitely generated, or it can be? It doesn't have to be.
It doesn't have to be in this definition. No.
Okay, thank you.
Yeah.
Except S, except the morphism S, it seems like those two are naturally defined because it's a K algebra, right?
No, it's the other way that's naturally defined. So there's always a map from any K algebra tensor itself to itself, which is the multiplication, and there's always a map the other way, the canonical inclusion of K into a K algebra. But
Okay,
these are
right.
special because they go the other way.
Right, thank you.
Yeah. Okay, so I guess it was Benjamin who pointed out that this definition is true for any K algebra, no assumption of finite generation. However, we'll be interested in the case where this K algebra is affine, so in other words, finitely generated and reduced, no non-zero nilpotents. And if we restrict our attention to those, so first of all, any linear algebraic group defines a Hopf algebra by this association, and this Hopf algebra will be an affine algebra. So we have this kind of map. At this point, I guess it's just a map of sets, and it's in fact a bijection because we can go the other way around. So I think last slide I had kind of squiggly arrows going one way, but we can also have squiggly arrows going the other way. And if you think about it, if you have an affine K algebra with a Hopf structure with these maps, then because it's an affine algebra, there's an associated algebraic set. That algebraic set gets the group structure from these maps. So that's why this is actually a bijection. And for those of you who like category theory, this is an equivalence of categories. Yeah, and also for those of you who like schemes, so there's a notion of affine group scheme, and that's just spec of any Hopf algebra, no assumption of finite generation or non-zero nilpotents. An absence of non-zero nilpotents, but those are just asides. I know category theory is not required for this course, so that's only for those of you who are interested.
Sorry, but you in this category you take morphism, for instance, for linear algebraic groups. Your morphisms are just algebraic morphisms, or also group homomorphisms.
Also group homomorphisms.
So also in the right-hand side, in the Hopf K algebras, there should be some axioms for homomorphisms between
exactly,
K algebras. Yeah. Okay. Thank you.
And I invite you to after the lecture to sit down and spell out what those axioms are precisely. But yeah, there is the notions of morphisms are important, and one must be careful. Okay, so moving right along. Oh yeah, so now let's get to so we've been talking a lot about theory and structure let's get our hands dirty with some examples of linear algebraic groups. So the first example is the additive group. So this is just the field thought of as a one-dimensional vector space over itself with addition, with the operation being addition. So so that's what it is. Let's translate the group axioms into what let's translate the maps on the group side into maps on the algebra side, on the affine algebra side. So first of all, what is the affine algebra of this additive group? Well, it's just polynomials in one variable, just the affine algebra of K, of A1. So what does the coproduct do, co-multiplication do? Well, if you think about it, so first of all, it maps from K brackets T, polynomial in one variable, to K brackets C, K brackets T, the tensor product. And that's just polynomials in two variables. Those two algebras are isomorphic. And this coproduct is pullback of functions. And when we trace through it, and we see that this just takes T to the sum of these two generators of the polynomial algebra. And if we think about the co-unit, it's evaluation at 0. So we take our polynomial here, and we just plug in T equals 0, and we get a number. We evaluate. We get a element in the field, and that's what. So this, when I write T maps to 0, that just means that what's happening here is this is all that's required to specify this map. It doesn't mean that everything goes to 0. It just means T goes to 0. And since this is, since eta is a K-algebra homomorphism and K brackets T is generated by T, that determines the whole map. So just to be clear about that. And what about the antipode? Well, the antipode takes T to minus T, and that again determines what you do for any polynomial. So if you have any polynomial, then it has it's a linear combination of powers of T linear combination of powers of T. We plug in T equals minus T and we get a new polynomial. So nothing happens to the even powers, the odd powers get a minus sign. And you can, so I won't go through it, but I encourage you to look back at the axioms for the Hopf algebra. So the claim is that these maps give K brackets T polynomials in one variable, the structure of a Hopf algebra. And to verify this claim, one needs to go through the axioms and check that they're satisfied. So that's something you can do. Okay. So that's one example. Here's another example, which is the multiplicative group. So if we think about K, the non-zero elements of K, then they form a group under multiplication. We can't include 0 because we can't divide by 0, but we can divide by anything else. So we have this group, and it's known as the multiplicative group. So one question for you guys. So this is like a pop quiz. So if so the claim is that this multiplicative group, so K star, the K minus 0, is a group, but in particular, the claim is that it's a linear algebraic group, but in particular, it's an affine variety. So true or false, K star is an algebraic, so is an algebraic subset of A1 of just K. So take I don't know, 5-10 seconds to think about it, and then I'll let someone answer. So again, the question is this K star, the non-zero elements of K, is that an algebraic subset of K? So I'll give you just a few more seconds to think about it. And as sort of a follow-up, well, okay. So first of all, does anybody have any thoughts to share about that? So is it true or false that it's an algebraic subset of K?
And I'm actually not sure if it's right, but if K is algebraically closed, then it contains, say, roots of unity, then it has torsion, but affine algebra is reduced. So, or maybe I'm mixed up. I think I'm mixing up something.
I think that's not quite the way to go. Maybe there's some argument there, but that wasn't the argument I had in mind. Anybody else? Okay, last chance. If you have any thoughts, it's fine. We're all learning here, so it's no problem if
I'm just wondering, in your question, do you mean if the set is closed in the heuristic topology? This is what
Yeah.
you asked. Then I think it's supposed to be open. The set.
Yeah, that's correct. It's open. It's not closed inside of A1. So if it's open, but so then we said before that affine algebraic varieties occur as closed subsets of like vectors of ANs. So then how is K star an algebraic? How is K star an affine variety, an algebraic subset of some Kn?
It can be regarded as an algebraic group of K2, like K x y minus 1.
Exactly. So we have, so as a side note here, side so K star is an algebraic variety, affine algebraic variety, via the following construction. So K star is the vanishing locus of xy minus 1 inside of K2. Okay, does that make sense to people? So that's how we, so it's a bit confusing because K star is naturally inside of K1, but it's only open in K1, it's not closed. And we want it to be closed somewhere. And in fact, if we look at this, if we look at K2, if we look at this polynomial, so maybe I should have said inside of K2, notes K functions on K2. I'm thinking about it as just polynomials in two variables. Sorry for the bad notation. I think there is some way to use LaTeX inside here, but I haven't figured it out yet. But we have to pass the K2 in order for us to see this, to see K star as a closed, Zariski closed subset of a affine space. Okay. Any questions on that? I don't want to dwell on it too much, but
can you specify the isomorphism between this and G and A1 minus 0?
Yeah, so maybe I'll just give you some idea of how the isomorphism works, and I'll let you fill in the details. But this vanishing set here can be identified with pairs of elements in K2 whose product is equal to 1. So if we have element in K2 that's two elements, it has two coordinates, let's say A and B, and this vanishing set is the set of all A comma B such that A times B is 1. So in other words, we can think of it as, so this means that that neither A nor B is ever 0, because their product is 1. So neither of them can ever be 0. So and that B is A inverse. So we just have A comma A inverse, and we know that A is never 0, but it can be anything else other than 0. So the isomorphism basically picks out this A. This vanishing set is just determined by its first coordinate. So that's the idea. I haven't spelled out everything, but I'll leave it at that. Was that helpful, Tal?
Yes, yes.
Okay. So let me just go through just say what the maps are, and then we'll take a break. So first of all, the co-multiplication turns into just product. So, well, oh, sorry. First of all, what is the affine algebra here? So the affine algebra is Laurent polynomials in one variable. So these are just like usual polynomials, but we allow for negative powers of the variable. So I just put plus or minus 1. Hopefully that's clear what I mean by this. And the tensor product of this algebra with itself is Laurent polynomials in two variables. And what the coproduct does is just take the generator here to the product of the generators on the right-hand side, and that determines the map. What the co-unit does is evaluate at 1 now, because 1 is the unit of the group, not 0 anymore. 0 is not even in the group. And notice that we can't really evaluate at 0 because a general Laurent polynomial will have negative powers of t, and we can't plug in 0 when we have t to the minus 1. So that's what the co-unit does, and the antipode takes the inverse, which we can do because this algebra has the inverse. So again, if you're interested, you can go through and check that the axioms are satisfied with these maps. Yeah, so I think this is a good place to take a short break. So let's come back in 5 minutes. Okay, so moving right along. So we did this. So far we've just done 2 examples. The additive group and the multiplicative group. I want to mention something about this is somebody asked about what the morphisms are. So homomorphism of algebraic groups from G to H is a group homomorphism. So we have to take the product of 2 elements in G goes to the product of the corresponding images in H. And it's also morphism of varieties, so a map of varieties like we talked about last time. Also, when we say that something is a closed subgroup of G, it means that it's a subgroup, first of all, but also closed refers to the Zariski topology. So closed subgroup of G will be a subgroup that's closed in the Zariski topology. So what are some examples of homomorphisms? Well, first of all, we just defined GM, and the claim is that for every integer, there's a homomorphism, group homomorphism from GM to itself that takes any element in GM, so any non-zero element in the field, to its nth power. So first of all, it's a group homomorphism because we just write it out. We note that GM is abelian, so the a product to a power is the product of the powers, and that's all we need. And it's also a map of varieties, and this is because it's induced from the following algebra homomorphism. So yeah, if you're not convinced, then you can go through and check that this is what induces the map from GM to GM. And yeah, this is obviously algebra homomorphism for any n.
Can you repeat GM?
Sorry?
Can you repeat the definition of GM?
Yeah, GM is, so yeah, it's fancy notation, but it's just as a first of all, as a set, it's just a non-zero element in the field, so K star, with group structure multiplication. And we also made a note that K star has the structure of an algebraic variety. It's isomorphic to a closed subset of K2. And this, yeah, GM, it just means M is for multiplicative. And yeah, does that answer your question?
So this is not the dimension or something. M
is not the dimension, no. So GM is always one dimensional.
Okay, thank you.
Yeah, and we also have GA, which is the additive group. That's also one dimensional. So M is just for multiplicative, A is for additive. Okay, and later, I guess we might not get to it today. Is there a question? Yeah, M stands for multiplicative. So we might not get it today because actually we're going slower than I thought, but we'll show that there's a bijection between, so any group homomorphism from GM to GM is of this form. So just going to a power, taking everything to a power. Okay, so maybe we'll get to that today.
I wanted to ask how about the exponentiation by n being a homomorphism. If it's defined in the Hopf algebra based off of the tensor product, and the tensor product is not commutative, is there some other, is the abelianness of GM modeled by some other property regarding these tensor products? Do we like make it a symmetric product or something?
So that's a good question. So you asked. So I think the tensor, first of all, so I'm trying to break down the question into pieces. So first of all, the tensor product, at least in this class, will always be just coordinate wise. We won't have any braidings or whatever. But the abelianness of the group is indeed reflected in the Hopf algebra associated to the group, and so the Hopf algebra is what's known as co-commutative. And maybe we'll mention that property later, but it amounts to, if we take, so the co-multiplication goes from H to H tensor H, and it's co-commutative if we do the co-multiplication and then we flip, that would be the same as doing just the co-multiplication. So there's a commutative triangle. So co-multiplication here and here, and then just a flip of factors. And Hopf algebra being co-commutative is equivalent to the group being commutative.
Okay, so they start off being like not commuting, but then we flip them one at a time until we get to x to the n, y to the n.
Let me think about what you're saying. I think it's, I think I see what you're saying. It's, yeah, I think that's right. So we take, no, I think that, well, yeah, maybe I think it's something not too deep. Maybe if you write it out, you'll see it. But I don't think I can explain it right away here. Let me think about it, and I can get back to you if you still have the question later on. Does that sound good?
Yep.
Okay, great. So okay, so we'll get back to this fact. I want to continue with the list of examples. So a very important example is the general linear group. So this is a affine algebraic group, a linear algebraic group. So first of all, what's a reminder about what the general linear group is? So we start with n by n matrices, and this is a n by n matrices is just k to the n squared. It's a affine space. It's just a vector space over k, and so it's a affine algebraic variety. And there's a map, the determinant map, and that's a polynomial map in the entries of the matrix. So that's a regular function on this affine algebraic variety. It defines an element of the affine algebra, and we set GLN to be the principal open set corresponding to the determinant. So it's, as I said, it's the set of all matrices with determinant non-zero. So again, we have this issue that, so the way I've defined it, GLN is an open subset of an affine. It's an open subset of the variety of matrices. So this does not actually define its structure of an affine algebraic variety. Does anybody have an idea of how to make it an affine algebraic variety? Just make sure I have the right notation. No takers? Okay, so the way we do it is we do a similar sort of trick to what we did with the with GM. By the way, GM is just GL1. So that's that, but GLN is the set of, it's the it's the vanishing set of det times x minus 1 inside, so where would this be? Inside k to the n squared. Yeah, so so k n squared plus 1, we think of that as a copy of n by n matrices and one more dimension, one more copy of k. And we have its algebra of regular functions. Those will be, first of all, we have the regular functions on the matrices, but then we have one more factor of k. So one more direct summand of k, of polynomials in one variable, functions on k. And that variable will be, I'm calling x. And so we have determinant times x, that will be a function on this whole affine space. And we take minus 1. GLN can be identified with this vanishing locus. Okay, so Yeah. Does that make some sense, or was that too fast?
I just want to clarify that I understand well. When you say affine algebraic group, you mean that you mean algebraic group that has a variety without the operation is affine, right?
Yeah. Mm-hmm.
Okay.
Affine,
No
maybe I said
relation
affine algebraic group. That's the same as linear algebraic group, which is the same as what you said.
Okay.
Yeah. Okay. So the operation on GLN is given by matrix multiplication. And if we think about its algebra of functions, its affine algebra, it's the following thing. So these are like the coordinates coming from, these are the matrix coordinates coming from each entry in the matrix. This is supposed to encode the determinant. So we have n squared of these t's indexed by I and j, each of them running from 1 to n. And the ideal quotient is the ideal generated by the determinant of these being equal to d. So we impose this relation. The determinant, which is just some polynomial of these tij's, is equal to d. So another way to think about it is we have our functions on matrices, which is just polynomials in these tij's, and we invert this element, the determinant. So as I pointed out above here, the determinant belongs to the affine algebra of n by n matrices. Okay, so far so good. And if we think about matrix multiplication and do the pullback of functions, like I was saying, then we obtain this equation, this map, and this determines the coproduct. So related to I think, was it Aria? I'm not sure how to pronounce your name, sorry. You were asking about commutativity and so forth. So the algebras we saw before were commutative, but were co-commutative, I mean, but this is not co-commutative because if we flip the factors, we don't get the same thing. Okay, and the co-unit is just given by taking Tij to 1 if I and j are equal and 0 otherwise. So this is the Kronecker delta. And the antipode, so the antipode is corresponding to inverses. So maybe this is what I've written here is kind of confusing, but if we think of these TIs as being like formal variables in a matrix, and then there's some formula that gives us the inverse matrix. There's some formula, it's just some polynomials in these Tij's. Each entry is some polynomial in the Tij's. And and Tij goes to the ij entry of the inverse matrix with these variables. So I use different, so I call them TAB as this, for the coordinates defining the matrix, and then taking the inverse. So the inverse matrix, each entry will be some polynomial in the TABs, and we take the ij entry of that, and that's what gives us the antipode map. All right, and then again you can check the Hopf algebra axioms. So yeah.
Okay, never mind.
Okay.
Okay.
Okay, so what does this look like when n equals 2? Well, it's easy to write down. Yeah, things are easier to write down when n equals 2. Then the determinant is, so if these are sort of matrix, these correspond to the entries of the matrix, then the determinant would be this function AD minus BC. And functions on GO2 is just this polynomial algebra localized at this element. We talked about localization last time. And Yeah, and then if you think back to the formulas above and you write them out in this case, then this is what you get. So this is kind of what you would expect when you, yeah, you basically get this when you do matrix multiplication. So this is the top left entry of the matrix with entries A, B, C, and D. This is the top right, and so forth. Okay. And what's the antipode? Well, it's kind of just, it's supposed to encode the identity matrix. So A goes to 1, B goes to 0, C goes to 0, and D goes to 1. Same sort of thing with the antipode. So if we think about the inverse matrix, it'll have D minus B minus C A. We also need to divide by the determinant. So that's what I have here. At first I wrote divided, but then this could be some, yeah, it's better because we're working in some abstract field to write it this way. It's still commutative. As an algebra, it's still commutative, so it doesn't matter. The order doesn't matter. Okay. Is that good so far? Any questions? All right. Okay, so now we just did GLN, and an important source of groups. We'll see later that every group, every linear algebraic group is such, but an important source of linear algebraic groups are closed subgroups of GLN. So first of all, if any closed, I should have said this earlier, but if we have a linear algebraic group, any closed subgroup of that linear algebraic group will be, again, a linear algebraic group. For open ones, it may or may not be true. Subtle things could happen, but for closed ones, it's all fine. So what are some closed subgroups of GLN? Well, we have a bunch of finite subgroups of GLN. All those are closed. So for example, the symmetric group, which acts as permutation matrices, we have a bunch of we have like the dihedral group, a bunch of finite reflection groups, and yeah, and in fact, every finite subgroup, if we think about its action on its group algebra, this is something I'll mention a bit later, appears as a subgroup of GLN. Okay, so we have finite subgroups. We have diagonal matrices. So yeah, pretty straightforward. We just have the subgroup. This is a subgroup, first of all, and it's a closed subgroup of diagonal matrices. So all the entries are in K star, and this is actually just the product of n copies of the multiplicative group. And this will actually, we'll also refer to this as the torus. We'll talk about that later. So an algebraic torus is just a product of multiplicative groups. Then we have the unipotent upper triangular matrices. So we have ones along the diagonal, and we have anything we want above the diagonal and zeros below the diagonal. So these are unipotent. Unipotent refers to the fact that the eigenvalues are all 1. So this is a subgroup. It's yeah, it's not a normal subgroup, but it's a subgroup. And if you think about it as a variety, it's homeomorphic to k to the n choose 2, but the group structure is different. So we can think of k to the n choose 2 as a product of additive groups, so GA to some power, and with sort of coordinate-wise addition. But in this group, the addition is not coordinate-wise. So these are coming from the entries up here because we can have anything we want in these entries. But the group structure is different. It's an extension of additive groups, but it's not a product of additive groups. Okay, so those are the unipotent matrices, and we also have the upper triangular matrices. So B will stand for Borel, more on that later. But these are kind of like the unipotent ones. They're upper triangular, but we allow anything on the diagonal. And since the determinant will be the product of the diagonal entries, we need that all these entries along the diagonal are non-zero. So in fact, this will be a semi-direct product. So UN is normal. It's not normal in the whole group, but it's normal inside of BN. And we also have the diagonal matrices, and we have the semi-direct product structure. Okay, so then we also have the special linear group, which is just matrices with determinant 1. We have the orthogonal group, defined by this condition, x transpose x equals 1. So yeah, all the columns are orthonormal. They form an orthonormal basis. And there's also the special orthogonal group, which is the intersection of SLN and the orthogonal group. So these are orthogonal matrices with determinant 1. And there's a symplectic group, which is defined using this matrix J. And the condition is x transpose Jx is equal to J. So maybe you've seen this in other classes. So this was example 4, I guess, an extended example with different parts of some closed subgroups of GLN. And we'll talk more about these subgroups. So these will be kind of a testing ground for some ideas that will come later. Okay, I wanted to mention one more example. So we've been talking, so all these examples so far have been linear algebraic groups. In other words, algebraic groups where the underlying variety is affine. I wanted to mention an example of nonlinear algebraic groups, and these are elliptic curves. So they're algebraic varieties with the group structures. They're algebraic groups. They appear as certain closed subsets of P2, but they're non-affine. So they're not linear algebraic groups. So this course will be about linear algebraic groups. Maybe we'll discuss elliptic curves at the end of the course if there's time, and abelian varieties and some more algebraic geometry. But for the most part, we'll focus on linear algebraic groups. All right, so here, I think I've already posted these exercises on the website, but these are nice ones to get used to. Examples of linear algebraic groups and working with them. Okay, so any questions?
Is there any relation between the names, linear groups and general linear groups and such?
Yeah, there's a reason they're called linear algebraic groups. So we'll see in a bit. I was planning on getting there later today, but I think it'll be next time, that any linear algebraic group can be embedded inside of GLN. So kind of GLN is the general linear group, and any when I say embedding, closed embedding, and any other linear algebraic group appears as a closed subgroup. So that's something we'll prove probably next time. That was what you were asking about, right, Tom?
Yes.
Okay. Okay, so okay, so we have, I actually need to go a bit early today, so we have about 10 more minutes to discuss. So let's talk about some basic results about linear algebraic groups. So the first thing is that there's a unique irreducible component, G circ of G, that contains the identity element of G. So the identity element is only contained in a single irreducible component. We saw last time that these irreducible components could intersect in a general variety, algebraic variety, but the claim is that here the identity is not contained in the intersection of any two irreducible components. There's a unique one that contains the identity. And in fact, this identity component has a structure of a group itself, and it's a closed subgroup of finite index in G. Yeah, finite index in G, that should say. Okay, so let me give a sketch of this proof. So for the first part, so we're trying to show that there's a unique, yeah, I guess you can almost still see it there. There's a unique irreducible component containing the identity. So let's suppose that there are two irreducible components containing the identity. And you can argue that that if we take those two components, if we apply the map mu to their product, then we get some subset of G, and when we take the closure, it'll be irreducible. So I think this was one of the results I mentioned earlier today. I'm not gonna prove it, but it's an algebraic. It's actually just sort of point set topology thing. But the closure of the image of X cross Y is an irreducible component of G. But since the identity is contained in both X and Y, so first of all, since the identity is contained in Y, we have that X must be contained in this image, in particular in the closure. And since the identity is contained in X, we have that Y must be contained in the image. So because if we have the identity cross Y, that will just map to Y. And X, little x, the identity will just be mapped to little x. That's all that's happening there. And since these are both contained and they're both irreducible, so since X is contained in here, and by hypothesis X is irreducible, we have an equality here. Same thing with Y. We conclude that X must be equal to Y. Okay, so that's the argument for the first part of the proof, that there's a unique irreducible component. Now, what about the second part of the proof? Well, first let's show that G-circ is a subgroup. Well, if we look at the image, so we need to say that show that it's closed under multiplication. So if we look at the image of G-circ cross G-circ, that image must be irreducible because G-circ itself was irreducible, and one is contained in the image because one is contained in G-circ. By part one, we see that it's everything, that it's all of G-circ. Okay, so that shows that it's closed under multiplication. So we also need to show that it's closed under taking inverses. It's the same sort of argument. Look at the image of G-circ under this inverse map and use part one. It's closed, and that's just because all the irreducible components are closed. That's something we discussed briefly last lecture. That's true in any algebraic variety, that the irreducible components are closed. In fact, in more general, something like Noetherian topological space, you have that all the irreducible components are closed. And what about normality? So this is kind of a cute argument here. So if we take any x and g, we look at the conjugate, and the conjugate has to be irreducible because it's just image of under this. Yeah, it contains one, and it's the image of an irreducible subset. I think that's all we need to argue that's irreducible, or maybe there's something more. But in any case, because it contains one, because one is fixed under conjugation by any element, we have this equality. Okay, so what about the finite index part? Well, we know, so then it follows that if we think about this quotient by this normal subgroup, it's equal to the number of irreducible components of G. So that follows from one. So I didn't spell it out here, but if we had any element in little g inside of the group, we can translate it. We have this sort of translation that we can multiply the whole group by little g, and that takes I guess multiply the whole group by little g inverse, and that takes g to 1. And there's a symmetry going on here by the uniqueness. So that shows that for any given element, there's a unique irreducible component going through it. So in particular, the irreducible components are disjoint, and they're parametrized by this quotient. And the number of irreducible components in any algebraic variety is finite. So that shows the finite index property. And as a corollary, so we get a quick corollary of this. So the irreducible components of G are mutually disjoint. I think I already said how that goes. And this quotient G mod G circ, the component of the identity, it's the zeroth homotopy, quote unquote, group. So in this setting, it's actually a group. And for a general topological space, the zeroth homotopy, quote unquote, group is not a group. But since G itself is a group, then the zeroth homotopy group is a group. So it's kind of cool. Anyway, I don't know if you appreciate my sense of humor, but that's what happens. And so basically the component set of components of G has a group structure, and that's just this quotient group. Maybe I say something. Yeah, I think this is.
Can I ask a question about the proof?
Yeah.
So just at the start, you said the x is contained in u of x times y bar.
Mm-hmm.
So maybe it's trivial, but in order to deduce that they're equal, we also have to see that they have the same dimension.
No, because they're irreducible. They're both irreducible.
But a curve contains an irreducible curve contains a point, and which is also irreducible, but they are not equal.
Do we need to show that they're the same dimension? I think well, they're both irreducible components. Yeah, they're not just irreducible as topological spaces, they're irreducible components of G. And so irreducible components, I believe, you're putting me on the spot here, so this is something to double check, but I believe they're all the same dimension.
I think that the irreducible components have to have maximal dimension in the chain.
Maximal dimension.
If you take all the irreducible sets, then a component is one that is maximal in a chain of one that I don't know how to explain it better.
Yeah, so irreducible components are the maximal.
Yeah, I see it now, that since X is an irreducible component, that it follows. But if I may also remark that since G is smooth, because it's homogeneous and every algebraic variety has smooth points, we can also immediately conclude that the connected components and irreducible components are the same. So it is impossible that they intersect a priori. So only one contain the...
Yeah, I guess we haven't talked about the fact that G is smooth.
Yeah, no, just a remark. I was just wondering about this inclusion, but okay, thank you.
Yeah. Okay, thanks for pointing that out and making sure everything's clear and complete. Okay, so I think this may be a good stopping point for today. So there's this argument about why they're disjoint. It's pretty straightforward. So if there are two that contain a little G in the intersection, then we translate them so that the intersection of the translates contains one, then we can conclude that they're the same. Okay, and there's some exercises here to look at. So yeah, I think this is a good stopping point for today. Any quick questions? Okay, if not, then I guess see you next week. Feel free to email if you have any questions. If you want to submit the exercise from last week, then please do so by Monday. And yeah, I'll email you if there's anything else. Thanks.
Thank you.
Thank you.